All right, so you can write that question down, underneath maybe where we were doing our little chart the last day. Hopefully on that last example, as you were working along with me, you can make a note that, or you just put a little X through it. I know it's going to cause some of you organizationally, I don't know, you people who like colors and organization, putting an X through that last example is going to be very painful for you, I know. You're good, then you're okay. That last example, remember when I switched the DI and the DO, I had a negative in there for the distance to the object, and that doesn't work. You can't put an object in behind a mirror. That's not the way the universe works. So that question was no good. So Jane places and you know what, to be honest, these examples, I just did a Google search to find some examples, and they had students' names in it, this person, so I just, so we're going with Jane, right? Jane places a 4.75 centimeter tall light bulb a distance of 33.2 centimeters from a concave mirror. If the mirror has a focal length of 28.2 centimeters, then what is the image height and the image distance? Okay? So when you get a word equation like this, or a word problem like this, the key is to figure out what our variables are, okay? And remember we have variables, I was going to write it on the chalkboard, but I'm going to write it here. Remember we have variables like distance to the object, DO, height of the object, HO, distance to the image, DI, height of the image, HI, and magnification, okay? So a 4.75 centimeter tall light bulb, what is that? What variable is the 4.5 centimeter tall light bulb? Which variable is that, do you think? Thomas? HO, thank you. I'm gonna pick on some other people because I think you get the idea, but that's good. Thank you very much. The object is obviously the light bulb, and that's the height of it. So HO is 4.75 centimeters. Excellent. How about some other information? Somebody tell me another piece of information in there as you read along. What does some of that next information tell us? Hands up. Yep, go ahead there, Sean. So the distance from the light bulb to the mirror, DO, 33.2 centimeters. Excellent. DO, 33.2 centimeters. Nice. What other information have we got there? What is that last bit of information? Yep. Yeah, so that's F, 28.2. Correct, the focal length. F, 28.2 centimeters. Okay. So which equation do you want to use first? We eventually have to get the image height and the image distance. It doesn't necessarily have to be in that order. What equation should we use first? We can actually only use one because we've only got so much information here. Which one am I going to use? Di over dou equals what? Negative di over dou equals? You could actually go look back in your notes. It wouldn't be a bad thing. 1 over di plus 1 over dou is 1 over F. I've got F and I've got dou. So 1 over di plus 1 over do is equal to 1 over F. Again, calculators need to be out. Again, the key to doing these is to know how to use the inverse button. They're going fast. Don't bump my cart. Don't bump my cart. Oh, Logan. Phone calculators might work as long as it's got an inverse button. All right? So, image distance, 1 over di plus 1 over 33.2. Notice I don't put the units in. All right? Some teachers, and maybe This is a better way to do this, right? Many teachers will say, make sure you include your units in the equations, and then they'll take little marks away if you don't put your units in, and some can be very picky about that type of stuff. And you know what? It is a good practice, but I'm not that concerned. There's a reason why I leave the units out. What do you think the reason is why I can leave those units out? There's a reason why I don't have to think or worry about the units. What do you think that reason is? Look at the units that are on there. They're all the same. If I had a meters and a centimeters, then I'd have to be concerned. I'd have to get them into the same units, and that's important. But because they're all the same, we know we're dealing with centimeters. We're going to end up with centimeters in the end. So 1 over 33.2 equals 1 over 28.2. As I rearrange, 1 over di equals, I'm hoping we can do this mathematically. We know that when we bring this to the other side, it's going to become a negative. 1 over 28.2 minus 1 over 33.2. And in the end, I'm going to just put therefore di equals. Now, if we were doing this with common denominators, we'd have many more steps. But again, I've taught you how to use the inverse button. So remember the way it's working. 28.2 inverse minus 33.2 inverse equals. So we know what that subtraction is. Then inverse again. Because remember, that's equal to 1 over di. We got to inverse one more time. Okay? We got some checking. What did you get? 187. We got supporters on that. Again, I'm not doing the calculation. We like it. 100. Sorry, what was it? 187.2. 187.2 centimeters. Notice it's positive, right? That means that image is where compared to the mirror? In front of it or behind it? It's back out in front of it. That actually tells us the type. If it's out in front, what type of image is it? It's real. And Thomas is still jumping out with the answers. That's okay. Real. Now that's not part of the question, but it doesn't hurt to think about that. It's real. All right, let's keep going with the magnification. Actually, you know what? I'm going to show you one more trick. It doesn't ask us for the magnification. So we could simply do this. Magnification is equal to, all right, negative di over dou equals hi over ho. I don't need to find the magnification. It doesn't ask for it. So I could just use that ratio to get my height of the image. So I don't have to actually get the magnification and then use the equation. I could actually use that equation in one shot, right there, just like that. It doesn't ask for the magnification. Negative, doesn't matter which number the negative goes with. What is the di? We just calculated that. 187.2 divided by do, 33.2 equals. We're trying to find the hi and the ho, 4.75 centimeters. We're doing some mathematics, multiplying both sides by 4.75. I think we've seen that before. I'll write it in with a different color, times 4.75. That cancels that out. I'll put it in brackets over here, times 4.75. That cancels that. hi equals. Now that's not a subtraction, folks. Let me put some brackets around here to make sure everybody understands. That's a multiplication. That's that -1 on the front of that equation. Notice there's one negative in there. There's not two negatives, there's just one. That tells me the answer is going to be negative. When I solve that myself, I use a combination of a couple of rules. I say to myself, that's going to be negative, so I'm going to put it because there's one negative in there. And then I just do the calculations and I don't put a negative in my calculator because I know it's going to give me a negative number. Then I'm going to write the number. 4.75 times 187.2 divided by 33.2. What'd you get? Negative 5.64? No, we don't like it. We like it? No, you're getting a lot of no's. Okay. What do we get? Negative 26.8? Negative 26.78, so we'll round that to 8. Okay? Centimeters? Did you solve your issue? Did you figure out what you did? Okay, good, good. Yep. Yep. No, that's okay. The difference is you would have rounded it to 1 decimal here, right? Then you would have done another calculation, and that because you rounded once and then twice, that changes that number just a little bit. It's not a mathematical error, it's a rounding situation. Yours is just as correct as the other one. It's fine, doesn't matter, okay? Negative. What does that tell me about the image? It's, nope, doesn't tell me it's virtual. I know it's real up here because it's in front of the mirror. What is the height of the image? If it's negative, what does that tell me? It's inverted. It's inverted. Inverted. All right? Location of it? Well, location is when we find the DI. That's the location. That's a very specific location. All right? Size. What's the size of the image compared to the object? Size. If we're just talking the terms that we learned for salt. Yeah, bigger. 26.8 compared to 4.75. Okay? So it is inverted and larger. All right? So we can get all that salt stuff from that. I have 2 other examples, but I'm only going to do 1. And that's because when I do the scale diagrams, they will be very similar. Hold on, don't write this down yet. Johnny quite concerned about pimple on his chin. What a silly question. Why did I even write that down? Blah, 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 blah. Go to millimeter-sized pimple. That's hilarious. Okay, Christmas tree ornament with a diameter of 16 centimeters serves as a convex mirror. I like that one. Let's do a Christmas ornament instead of, I don't remember the guy's name. Johnny's pimple? All right. Let's worry about a Christmas ornament instead of pimples here on a Friday today. The Christmas tree ornament. I'm sure we've all done that before. Put an ornament on the Christmas tree, and then notice that you can see your face in the ornament, right? You get really close, your face is all distorted. It's all kind of funny. So that's what we're talking about. We're talking about a Christmas tree ornament with 16 centimeters in diameter, serves as a convex mirror surface on the outside. Determine the image size and the image distance of a 1.6 meter tall child standing at a distance of 2.8 meters away. What is that a concerning question? The look on your face, Taylor, makes me. At the question? Oh, that's more entertaining than Johnny's pimple? Oh, you mean a 1.6 meter tall child? I never thought of that. Again, I cut and pasted it. This is a huge child. Are you kidding me? This is a monster child. The 5-year-old at 1.6 meters tall. Puts them about there. What's that? I'm 1.8. Gonna go with an estimation of this. It's a big kid. All right, it's a big kid. Don't make fun. Okay. Well, let's start to decipher some of our variables. What do we know here? Tell me some of the information. Ideally, I'd like people to raise their hand instead of you know, people shouting out answers, but, you know, that'd be ideal. Some data here. What do we got? Yep, John? Yep, excellent. HO. That grossly huge child. What else? More variables, more data. Yep. BO 2.8 meters. All right. Well, that last bit of information about the ornament itself is where we're going to get our last thing. What do you think that data is ultimately going to get us? That physical shape of the ornament. What is that eventually? Which of our variables am I going to write here that we're going to ultimately get there? It's going to be F. Let's think about this. The ornament, listen folks, the ornament is 16 centimeters in diameter. All right? If I divide it in half, what do I get? So if I divide it in half, I have 8 centimeters as R. The brain can function without verbalizing it. I know that's the way your brain functions, but anyway. All right, Thomas, what am I doing? Why am I dividing it in half again? To get the focal length. Therefore, F is equal to 4 centimeters. We do need it in meters. We need to have them all in the same units. What would you like to do? What do you want to convert? Meters into centimeters? I'm in agreement. I like meters to centimeters. That's going to give me some big numbers over there. Are you, is what 28? With conversions, I know. We had this discussion at the end of class. Ashley, you do not get to answer about conversions right now. You just listen. Okay. No. We don't need a chart. We don't need a chart. How many centimeters in a meter? 100. I'm simply, listen folks, listen. 1 meter equals 100 centimeters. I'm going to move it 2 places, or I'm going to multiply this by 100. Stop talking. 160 centimeters. 280 centimeters. 4 centimeters. Now we can do the problem. It's not supposed to be this hard. Okay, 1 over DO plus 1 over DI. I'm ignoring all of you. I am in my own little teaching bubble. And beyond this bubble, I hear nothing. There's the best students in the world. Excellent. Good work, students. Way to convert that. Nice job. Let's continue. 1 over 280 plus 1 over DI equals 1 over 4. Oh, what did I do? It's usually 1 over DI, 1 over DO, right? It doesn't matter to the order, by the way. Do you notice what I did there? It doesn't matter which one comes first. All right, that's just me writing it down. You're okay. 1, again, I'm not hearing anything. All I hear is perfect students sitting there listening quietly. 1 over 4 minus 1 over 280. Again, we're using the inverse procedure. We're not worrying about Common denominators. Distance to the image. I'm concerned about this. No, it's not. Ah! No, we do have a mistake here. I know. Does anybody know why? Has anybody figured out why I'm concerned? Has anybody figured it out? We have missed something here. We have missed something. It's a tiny little thing. It's exciting. This is exciting. The reason I'm concerned is, no, that doesn't concern me. Listen, folks, hey, listen up. Listen, in the end, you're getting a DI that's positive. And when you look in a convex surface with my child, 1.6 meters tall, all right, it should be a smaller image, and it should be virtual, like looking in one of those big mirrors in a hospital, et cetera, et cetera. Okay. What did we not do in our data here when we were told that this was a convex surface? We have one tiny little mistake in our data. One tiny little mistake. Who's going to find it? It's an easy, we can find it. What's that? The focal length is negative. When we have a convex surface, the focal point is behind the mirror in the virtual world, meaning this is negative. Now hold on, that doesn't change much. What that does is it simply puts a negative there and a negative there. All right, so if you didn't write down your answer, you don't need to scribble anything, you just have to add a negative. So now you're doing -4 inverse minus 280 inverse. And you should get a negative answer, which puts it in behind the mirror. That's what we needed. Negative 3.9 centimeters. Excellent. Excellent, excellent. All right. Negative puts it behind the mirror. So what type of image is this? If the image is behind the mirror, it's virtual. And for a convex, we need it to be virtual. They only produce virtual, right? So if you have a good understanding of how the mirrors work, you can catch those problems when they come up. And again, we can use, if we want the height of the child in the image, then we can again go negative DI over DO, and we can go straight to HI over HO, or you can calculate the magnification. It doesn't matter how you do it. Makes no difference. So negative, what is the DI? Negative of a negative. Negative 3.9 over DO was way out there, 280, equals HI, that's what we want to find, and HO is that grossly large child of 160 centimeters. And so we're going to bring that up to the other side, just like we did a minute ago. We're going to times 160 to get rid of it. And again, we're going to times 160. I'm going to put that little negative in brackets. So here's the way I'm thinking about it when I look at this question. Those two negatives are going to cancel each other out. So I'm going to just do 160, 3.9 divided by 280, and that should do it for me. HI equals. We got a number? 2.2. And that's in centimeters, 2.2. Because remember, you're looking into an ornament. So you're looking at a tiny little, picture of yourself in the back end of an ornament. That kind of makes sense. What's that? It's much smaller. Yep, much smaller. Much more manageably sized child? No, at 2.8 centimeters? No, that's way too small. Let us continue. So I told you about the worksheet already yesterday. I hoped to get to this point yesterday, but I didn't, but that's okay. So that worksheet is some practice to do on that. I'm now going to talk about something called scale diagrams, and then I've also assigned an assignment, which is going to be practice of this and drawing a scale diagram. So I'm going to be showing you right now how to draw scale diagrams. I'm going to stop my recording here first before I entertain any questions, because I don't need to record the scale diagram thing. And so let me just stop that recording.